Hello. In today's video we're going to be looking at pH, pOH, for either known concentration of hydronium and hydroxide or when we have strong acids and strong bases, and then we're going to use the idea of pH and pOH to calculate out our hydroxide and hydronium concentrations. We're also going to look at acid-base strength, and within weak acids we're going to look at its strength based on its conjugate. Okay, so first let's look at what pH is. It is a measure of acidity, so it basically tells us how much acid we have or hydronium we have in our solution. And the greater the hydronium concentration, the less or the smaller the pH. So as hydronium concentration goes up, pH goes down. We could also use the idea of pOH. pOH measures basicity. Sure if that's how you spell it. Let's try that. There. Basicity. So the greater the hydroxide concentration, the lower the pOH. We have the following calculations. So pH is equal to negative log H3O plus, or pH is equal to negative log H plus if we are not in water. pOH is the negative log of our hydroxide concentration. Okay, the pH and pOH scale are generally between 0 and 14. So if you have a very, very basic base, you can get a pH that is greater than that 14. Okay, or a very, very acidic acid, we can get a pH lower than 0. So we're basically looking at how much of the substance we have. So using these calculations, we can also take and go the other way, take 10 to the both sides, and we can get a calculation of hydronium or hydroxide if we already know our pH or pOH. Okay, so for a solution to be acidic, basic, or neutral, it depends on our amount of hydronium and hydroxide. So for a neutral solution, we'd say that our hydronium concentration is equal to our hydroxide concentration. And if we're at 25 degrees Celsius, each of those will be equal to 1.0 times 10 to the negative 7. Right, so multiply that together. 1 times 10 to the negative 7 squared will give us 1 times 10 to the negative 14, which is our kW. So if we have a hydronium concentration of 1.0 times 10 to the negative 7, we have a pH of 7. If we are talking about an acidic solution, we have more hydronium than hydroxide. So our hydronium concentration will be greater than 1.0 times 10 to the negative 7, while our hydroxide concentration will be less. They will still multiply to give us 1.0 times 10 to the negative 14, But as we increase our hydronium concentration due to the Le Chatelier's principle, we would shift back towards water. So this will decrease our hydroxide concentration. And if we were to do that, do our pH calculation, we see we have a pH that, since we have a greater than 1.0 times 10 to the negative 7, we have a pH that is less than 7. For a basic solution, we have more hydroxide than hydronium. So our hydroxide concentration is now going to be greater than 1.0 times 10 to the negative 7, while our hydronium concentration, due to Le Chatelier's principle, will be less than 1.0 times 10 to the negative 7. So again, this is a shift. If you increase one, you're going to have to decrease the other. And our pH here would be greater than 7. However, our pOH would be less than 7. Okay. We can relate pH and pOH to each other if we remember Kw is equal to our hydroxide concentration times by our hydronium concentration. So those two are equal to 1.0 times 10 to the negative 14. And if we take the log of both sides of this, we can get log OH plus log H3O plus gives us negative 14, as log of 1.0 times the negative 14 gives us negative 14. We're going to multiply everything by negative 1, and we would get 14 is equal to negative log hydroxide concentration minus log hydronium concentration. And hopefully you recognize that these right here are pOH and pH. So I would say that 14 is equal to pOH plus pH. So we can very easily determine one if we have the other. Now, as a note, if you have a strong acid or a strong base, they will completely dissociate to produce hydronium and hydroxide. So we can figure out our hydronium concentration by just taking our acid concentration. So if we have our acid concentration, that will be equal to our hydronium concentration. There is another note here, though. Not the same for a diprotic, or for the diprotic acid H2SO4, as there is a second ionization. Okay, and then our base concentration. If we have our base concentration, it's a strong base, we can figure out our hydronium concentration by, our hydroxide concentration by taking that base concentration, multiplying it by our N value, and that will give us our hydroxide concentration, where N is equal to the charge of the metal ion in the base. Alright, so something like CaOH2 has a N value equal to 2. Okay, let's try a couple of examples, see how we're doing with the concepts here. So, we've got vinegar. Vinegar has a hydrogen ion concentration of 3.0 or 3.7 times 10 to the negative 3. So this tells us that our H3O plus concentration is equal to 3.7 times 10 to the negative 3. And we want to calculate pH and pOH. So pH is pretty easy. We say pH is equal to negative log H3O plus. So it's equal to negative log 3.7 times 10 to the negative 3, which gives us a value of 2.43. And remember, our pH plus our pOH sum together to give us 14. So if we take 14 minus 2.43, we will get our pOH, which is a value of 11.57 in this case. Okay, now we've got a pH equal to 10.5, and we want to know what our hydroxide and hydronium concentrations are. So to relate pH and concentration, remember that 10 to the negative pH is equal to our hydronium concentration. So our hydronium would equal 10 to the negative 10.5, which gives us a value of 3.16 times 10 to the negative 11, which is a very small value, but that is to be expected as we have a basic solution. And now we can just take that value. Remember that Kw is equal to our hydroxide concentration times by our hydronium concentration. So if we take our Kw, divide it by our hydronium concentration, we can figure out our hydroxide concentration. So we take our OH minus, that'll be equal to Kw 1.0 times 10 to the negative 14, divided by our hydronium concentration 3.16 times 10 to the negative 11. Which gives the value of 3.16 times 10 to the negative 4. Last, we're looking to solve for the hydroxide concentration and pH for a 1.5 molar solution of strontium hydroxide. Strontium hydroxide, strontium is a group 2 element, so we know that this is a strong base, and as such it will completely dissociate to produce hydroxide and strontium ions. So it would look like this: SrOH completely dissociated into strontium ions plus hydroxide ions. So we can take our strontium ion concentration, multiplying by our N value, which is 2, to get our hydroxide concentration. So our OH minus concentration here would equal our strontium concentration, 1.5 times 10 to the negative 3, times by our N value, 2, giving us 3.0 times 10 to the negative 3 molar for our hydroxide concentration. And then we take pOH is equal to negative log 3.0 times 10 to the negative 3, giving us a pOH of 2.52. And then we could solve for our pH by taking our 14 minus our pOH, giving us 11.48. Okay. You could try these out on your own. You can pause this video real quick and try out a couple additional examples if you would like. But I'm going to move on to a quick review of acid naming. So we have two types of acids that we look at in this class: binary acids and oxyacids. A binary acid, we have one element plus hydrogen. And we could look at that one element. This would be an anion, and this would be our H+. So we add them together to get a neutral species. So our anion itself, we take its element name and we remove, we add in the ending "ic", and then we add the prefix hydro. So prefix hydro to the ending, or to the beginning, and then the suffix "ic" acid. So if we have something like this, this is bromine. So we'd add hydro to the beginning of it. Then we'd have bro, and then we add the ending "ic" acid. So hydrobromic acid. Okay. Oxyacids, these are our polyatomics plus hydrogens. And we're going to have enough H pluses to balance charge. Same thing up here. So, we do not have a prefix, so there's no prefix here. But what we do is we take our suffix of our polyatomic and we change it. So if our polyatomic has an ATE ending, it's going to become "ic" acid. And if we have an ITE ending, it's going to become "us" acid. As a note, we're not going to add a prefix, but if your polyatomic already has a prefix, you're going to keep that prefix in there. Okay, so an example of a polyatomic that has an ATE ending is nitrate, NO3 minus. So if we add in one proton, so take NO3 minus, add a proton, we get HNO3. So a balanced species. That 8 ending goes to "ic" acid, so this be nitric acid. Then we could look at NO2 minus as well. Add a proton in there, we get HNO2. That has an ITE ending, nitrite. It's going to go to "us" acid, so nitrous acid. Okay. So, just super quick review of naming. Okay, now let's look at our acid and base strength. So, first we're going to start with acids. Acids, if it is a strong acid, we will completely dissociate in water. So all strong acids completely dissociate in water. Sulfuric acid is the only one that has a diprotic, or that is a diprotic acid, and it will, the first proton will completely remove, but then we have an additional proton that also removes, so it's kind of weird. But here is our list of strong acids. Nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, perchloric acid, this is where we had a prefix initially and we left that prefix on. And then for our diprotic, we have sulfuric acid. But as a note, only the first proton is removed completely. As in, this is a strong acid and will completely dissociate, but this is a weak acid. So once it's lost that first proton, it becomes a weak acid, and then we treat it like a weak acid. Our weak acids, on the other hand, they're all the ones that aren't on that list of 7. So it's an acid that does not completely dissociate. Its dissociation is an equilibrium process. Again, any acid that is not a strong acid, we consider that a weak acid. But here are some examples. HF is commonly thought of as a strong acid, but it is not. So hydrofluoric acid is a weak acid. And we have our acetic acid. Phosphoric acid, another one that a lot of people think would be a strong acid that is not. And another common one, carbonic acid. Okay. Our strong bases are going to be bases that either release hydroxide during dissociation or pick up a proton. And remember, since it's a strong base, it's going to dissociate completely. Okay, so these are going to be our group 1 and group 2 hydroxides. Okay, like sodium hydroxide, calcium hydroxide, barium hydroxide, those type of things. And then the other one is those that they're anions that pick up protons. So something like NH2 minus, O2 minus, and H minus. So these are things that are highly unstable as an anion. So they're going to very easily pick up a proton. Okay, so we can relate our acid strength based on the conjugate that it forms, and vice versa. So if we have a strong acid, it's so strong that it dissociates. So its conjugate will not pick up a proton to go the other way. So it is going to be so weak we consider it a neutral conjugate, a conjugate that is neutral. So it would be what we call a neutral anion. Okay? So that anion will not pick up a proton to reproduce the acid. Okay. A weak acid produces a weak conjugate base. Upon proton loss. So we call this a basic anion. And it will hydrolyze water. Okay. And then we also look at a weak base. When it picks up a proton, it produces a weak acid, or weak conjugate acid. And this, we call it acidic cation. So it will hydrolyze water. Okay. And then, of course, if we have a strong base, it's going to dissociate to produce hydroxide and a neutral cation. Okay, so let's see how we did with these. We're going to look at each of our acids and bases and determine if they are strong or weak. So this first one, magnesium hydroxide. Hydroxide, that indicates that it is a base. And because magnesium is in our second row, this would be a strong base. Next one is hydrochloric acid. We said hydrogen right there. That hydrogen is indicative of an acid. And hydrochloric acid is on our list of strong acids. So this would be a strong acid. Next we have, what is this? Pentylamine, something like that. So here we see a nitrogen. Anytime we see a nitrogen, that is a base with a pair of electrons. So we consider this a base, specifically a weak base because it does not have a hydroxide. Now our next one, H3PO4. We see that hydrogen again. In the case it's an acid. This is not on our strong acid list, so this is a weak acid. Next one, hydroxide, indicates that it's a base. However, this is not a group 1 or group 2, so we consider this to be a weak base. Okay, here we go. Next one, HF. We see that hydrogen, indicating that it's an acid. Not on our strong acid list, so it must be a weak acid. Rubidium hydroxide. We see the hydroxide has to be a base. Rubidium's in group 1, so this would be a strong base. And then we have a hydrogen here, indicates it's an acid. That acid is not on our strong acid list, so this is a weak acid. Voila! Okay, that is everything for 4 and 5. We'll do one additional video to talk about our last learning objective, number 6. Okay, bye!